let's continue our discussions of very basics of the metaplectic group and the Weil representation. Okay, so in the lecture 2, basically I was talking about all different kind of again the realizations of Weil representation and the splittings, etc. So what is a metaplectic group? Okay. So recall last time we have mentioned we have two cocycles from the intertwining of the Heisenberg representation. So if you have so the logic is like let me start here. So the logic is that let rho and so you will have a symplectic space W. Okay, maybe let me my screen have some little problem. Okay, so you have a symplectic space with symplectic form. Then from this you will have the Heisenberg group, which is W cross F. Then from this you will have the the Heisenberg representation. Okay, so you have additional theta, which is the psi. This is a non-trivial additive character from F to C1. C1 is all the complex number of modulus 1. Okay, so for this psi, you can you have a unique irreducible representation of the Heisenberg group called rho psi S, so the symplectic group will act on the Heisenberg group by only act on the W part. Okay, so then this will like intertwine. So for each G, you will have an intertwining operator intertwines the Heisenberg Weil representation. So, but this intertwining operator is unique up to scaling. So therefore, you collect the collection of all G and M, where M are the intertwining operators. Okay, so we call this metaplectic cover, C cross cover of the symplectic group. So we will have a short sequence like this one goes to MP W psi S, C cross goes to SP W goes to 1. Okay, so this short sequence. This is a C cross covering, and so we also have C1 covering, because you can always this Heisenberg representation is unitary representation, so you can require the operator to be intertwining operator to be a unitary operator. So therefore, so we have a C1 extension of the symplectic group. So this is, I'll give you 1 goes to C1 goes to MP W psi S C cross and SP W goes to 1. Okay, and we see that suppose under the Schrodinger model. Okay, so this S is realized as a Schrodinger model. So then we will have a natural cross-section of this split this short sequence, which called R. So that is send any G in SPW, G in SPW to RG. So this is some kind of integration operator on the okay. So then you can compute the cocycle and of this section. The conclusion is that this cocycle so this cocycle is called the Larry cocycle, and the cocycle take value in mu8. Okay, so this one is take value in mu8, which is taking the value of 8th root of unity in C cross. Okay, so once you have this cocycle, then you can abstractly define a group abstractly define a group which consists of SPX and across, say, as a set. And then the multiplication is given by this formula. This is a general factor for the group extension. As far as you have a 2 cocycle, you can define an extension. Okay, so as far as this say contains mu8, then you will have this group. Okay, so therefore, the Larry cycle tells us you can define at least the 8th covering of symplectic group. Okay, and so, but on the other hand, you also have a cocycle called the raw cocycle. This is another section to MP, which consists of beta XR. Okay, so recall that last time we have this kind of very complicated defined beta, and then we have this raw cocycle. This is raw. This is Larry. This is raw. Like differ by the boundary of this beta. And the point is that this cocycle takes value in mu2. Okay. But okay, right. So therefore, you can, for any subgroup of C cross which contains mu2, which is just plus minus 1, you can define an abstract group consists of SPW and C, such that it is given by this cocycle. Okay. Of course, every a priori this kind of construction depends on your choice of this, actually not only X but the polarization of W. Okay. So the natural question is that what's the relation between this group, this abstractly defined group, and this abstractly defined group? Okay. So because we know that this Larry cocycle is cohomologous to the Rao cocycle, so we know this two group is isomorphic. So do I need to explain the basic things for the group extension? Just how to classify the group extensions?
Yeah, sure.
Okay. So maybe, so in general, so I will talk about some, maybe a little bit. So so what is a group extension? It is just so suppose G is a group. Say G is an extension of A and B if there exists a short exact sequence. So from A to G and G to B to 1. Okay, so this is a group extension. So for each, then then we say that, say, 2 extensions are isomorphic if 2 extensions means A to H, B to 1. So if So there exists a diagram such that this is A, G, B goes to 1, and this is isomorphism. So then we say that's the extension of A is the extension of AB by the extension H and the extension G are isomorphic. Okay, so how do you classify the isomorphic extension? So for each extension, you take any section S. Any section S. So then this S will gives you a cocycle. So that's C1, G, C. I think I should call B1, B2. This is defined to be S B1, B2, and the SB1, SB2 inverse. B1 inverse, maybe B2 inverse, B1 inverse. So it's measure the discrepancy of S to being a group homomorphism. Okay, if S is a group homomorphism, then this function is identically zero, identically 1. Okay, constant function, and so this one will give you an element in H2 of, okay, right. So somehow for the theory to works perfectly, we should assume that A is abelian. A is abelian. So then this C is an element in H2 of the group homology of of B with value in A. Okay, and if so, certainly the co-sections, you may have two different co-sections. So the difference between the two different co-sections are a co-boundary of, okay, so this is called a cocycle. So if you have two sections, S1 and the S2, then so S1 will give you C1 and the S2 will give you C2, and the C1, C2 are differ by, so C1 and C2 are actually differ by the element. Okay, by the way, this is actually an element inside the G, but because if you project, so let me call this is P. If you project this element to B, then it is trivial. So this means that this element actually can be viewed as an element in A. So therefore, this is an in A. So what is a element? What is a cocycle? The cocycle is basically a map from B cross B to A. Okay, so there's no reference to G actually. To classify the extension, there's no reference to G. It's just a function from B cross B to A. So just like our raw cocycle is okay, our Larray cocycle, this one CXi is SPW cross SPW to mu8. Okay, this raw cocycle is CX from SPW cross SPW to mu2. Okay, of course, if you have a group which contains mu8, you can view this cocycle as a map from SPW cross SPW to Z. It just by compose the natural embedding of mu8 to say. So therefore, right, it give you a cocycle. Okay, so this is from group extension, you have a cocycle, and then from the cocycle, so from cocycle, so if you have H2 of BA, so it is represented by a cocycle, then it will give you an abstract group called right. It will you just define a group on B cross A. Okay, so it will, how do I say it? So extension by the C as a set, it's just a B cross A. Okay, and then the group law with group law, which is B1, C, A1, B2, A2 is equal to B1, B2, C, B1, B2, A1, A2. Okay, so this is a group. You can check this is a group.
Prof, just to ask you, how does this differ, for example, from a semi-direct product?
This semi-direct product is the case, the cocycle is a trivial.
Trivial. Okay.
And okay, so and the two C1, C2 represent the same class if and only if EC1 is isomorphic to EC2. Okay, so this is the general theory. Okay, so right. So from the general theory, we know that these two groups are isomorphic, but whether these two groups are isomorphic to up to is this isomorphism unique, basically? So there's a general theorem which tells you that it is unique. Okay, in the most of the case. So we will so there's a notion called canonical isomorphism of extension. So if you have two extensions, we say these two extensions are canonically isomorphic if there exists a unique alpha such that makes this diagram commute. This is extension of G, so you can think G is SPW. Okay, so a general theorem tells you that if G is a perfect group means that G equal to its derived subgroup. Then all the extension, if two extensions are isomorphic, then they are canonically isomorphic. It means the isomorphism is actually unique. Okay, so the nice thing is that SPW is perfect in the most of the case, especially when it is perfect when W is defined over local field. Is defined over local field. Okay. Right. For example, SP. So real symplectic group, p-adic symplectic group, all satisfy this condition. For the finite group, in the most of the case, this SP2N FQ is perfect, except there's an exceptional case is SP2F3. Okay, so you can check this is not a perfect group in this way. So in general, the number of points in SP2N FQ is given by this formula. It's a Q to the power of N squared times product of from 1 to N, and this one. So you just substitute N is equal to 1, Q is 3, then you see it is 20, it has 24 elements. So therefore, okay, so it cannot be simple and it cannot be perfect. Perfect. So the smallest non-abelian simple group is A5, which has 60 elements. So now this group only have 24 elements. Okay. Right. There's another thing is that if you have two Schrodinger models, two realization of the Heisenberg group, Heisenberg representation, then you will have an intertwining operator T, which intertwines the Heisenberg action. In this case, you actually can define a isomorphism of MPWC cross with reference to the first realization of the Heisenberg representation and the second realization of the Heisenberg representation. Okay, so this you can explicitly write this map. It is maps G to G and then maps the intertwining operator for S to TMT inverse. Okay, so this is very simple. You just transfer the, so if you have S, you have N, so you have S goes to N. So this is T. So you just transfer the structure. You see that this T inverse MT is intertwines S prime. Okay. So it's just a transfer of structure. But this lemma tells you that this map is actually the unique map, which makes a diagram, right? Which makes a diagram commute. Okay, so I would like to say, let me add one more page. So you basically have this situation. It is 1 goes to C cross goes to MP. W psi SC cross goes to SP. W goes to 1. Okay, so then you have C cross goes to MP W psi S prime, C cross goes to SPW goes to 1. So you have this identity. So you have this kind of trans TSS prime. I would like to say this map SS prime. Okay. So this is a unique map, and it induces identity on SPW and induce identity on C cross. So therefore, this, okay, certainly you can check this is a group homomorphism. So therefore, these two extensions are isomorphic, and they are, because SPW is perfect in the most of the case, so this is a unique isomorphism. Okay, so you can do the same thing by replace C cross by C1. Okay, you can do the same thing. Right, so what is a metaplectic group? So, of course, you have a lot of different definitions, but I think the most simple way to define it is for any say which contains mu2, you can define it as the inverse limit of this MPW say rho. Okay. Right, you define in this way. So for each realization, you will have a metaplectic group, which this one is physically, it consists of G and the intertwining operators. Okay, such that satisfy certain condition. Okay, physically you have this kind of for each Heisenberg wave representation S, you will have this group. But because there's a unique canonical isomorphism between them, so you can like chain them together so that you consider, right, you consider the limit or either direct limit or inverse limit. There's no difference that you consider the limit of these groups. You define it to be MPWC. So the good thing for this kind of definition of MPWZ is that so it automatically gives you for each realization of the Heisenberg representation, it gives you the Weil representation. Because this is just so this is a subset of the product of all MPWC rho psi s. Okay, so you for abstract element G tilde here, so you will have a projection to a concrete realization of the metaplectic group. And then this concrete realization of metaplectic group will have, physically, it will contain a pair with the intertwining operator MS. So you just let this intertwining operator act on the S. So this is the metaplectic representation. So the Weil representation. Okay, so this is an abstract way to define the metaplectic group. Okay, just like how you define the abstract Borel, you take all the Borels and you identify them. Oh, how do you define abstract carton? So abstract carton of a reductive group. You consider all the pairs of maximal torus and Borel inside the reductive group, and there will be a canonical isomorphism between these pairs. So you glue them together using direct limit, you get abstract carton. Here is the same. You consider all possible realizations of Heisenberg representation and then glue them together. Okay, so in particular, for any two device K, so you can define MPWK, which is so this abstract abstract metaplectic group taking value in mu K. Okay, so there's a nice property for if you want to recover the usual double covering of the metaplectic group, is that you for any say contains mu2, you have this abstract metaplectic group, then you just take the derived subgroup of this metaplectic group. It will be, the derived subgroup will be a double covering of SP. Okay, so the logic, so the proof is very simple. So certainly this MPW say is the center say times MPW2. Okay, physically as a subgroup, it looks like this. So therefore, it implies that the commutator is, because everything inside the say commute with other elements. So therefore, it implies that the commutator subgroup of MPWC is actually contained in the commutator of MPW2, MPW2. Okay, but this one is certainly contained in MPW2. So therefore, we will have this one. This is just by so you can see this by calculation of the Raupo cycle. But on the other hand, so if the commutator is, so because this is a two covering, so if the commutator only has two cases, the commutator is a proper subgroup of MPW2, or the commutator is equal to the whole MPW2. Okay, if it's just a proper subgroup, then it must be isomorphic to SPW. So this contradicts to the fact that the covering is non-split covering. So because you can find a subgroup inside MPW2, which is isomorphic to SPW. Okay, so therefore you conclude that for any realization, the commutator of the full of the metaplectic group MPWC is actually a double covering. Okay, so I think so this proposition give you another way to define metaplectic group is you have this full metaplectic group, right? C cross even, like for any realization, then you can consider the commutator. So the claim is that so this one is a double cover. Of SPW. Okay, so I think this gives you the quickest way to define metaplectic double covering. Although it's very abstract, and this fact even holds for the modular case actually. Okay, so but anyway, the convention will be MP0 if the symplectic space is zero space. Then we define MP0 say to be just same. Okay, so yeah, I spent quite a lot of time to discuss how to define metaplectic group. Right, you see in the definition, you somehow need a symplectic space. But we would like to see if we change the symplectic space, what will happen. So one of the things is that you can change the symplectic space by similitude. So what's the meaning of similitude? If two symplectic space W and W prime are like similitude to each other, means that for any W1 and W2 inside W, TW1, TW2 under the pairing of W prime is equal to A times W1, W2, where A is a non-zero constant. Okay, so this is called a similitude. So it's certainly that you have a unique map from SPW to SPW prime by map G to TG T inverse. Okay, so then so you can define this define intertwining operator which called the phi ZT. Okay, I think just by translate this structure so that okay, so you have S prime, which is a rho psi, S prime, which is a Heisenberg Weil representation, Heisenberg representation of HW prime. So how to so as a representation, it also add on the same space as S, but you see that you have HW goes to sorry, I think I missed one very important point here. So the point is that okay, so if you go back to look at this Rauco cycle, so you see the Rauco cycle, this formula is nothing to do with the additive character psi. Okay, so this is one of the points. So therefore, you can eliminate everything related to psi. So therefore, this limit can take over even running over all possible psis, and then you have a unique isomorphisms between each of the concrete realization. Okay, so therefore, you see the metaplectic group here has no reference to the additive character psi. Okay, so then here we here we have, sorry, and here we have this kind of similitude. So therefore, HW prime W prime is isomorphic to HW by send let me see, I forgot to write, so hopefully I can recover this, but okay, so I should write W is isomorphic to HW prime, which send a W T to TW AT, I think. So you see, this is an isomorphism. So therefore, under the pullback, I think the rho psi S prime pull back with this, okay, let me call this phi t, pull back with phi t. So this is equal to rho psi A S. Okay, so this is a Heisenberg representation with psi A, but anyway, psi A is a character, additive character, which given by this formula. Okay, so but it doesn't matter that this psi t will give you an isomorphism from MPW, say, of psi S, psi A of S with MPW, say. It's getting boring, I think. Sorry for this. S prime. Okay, so therefore you will have this unique isomorphisms here. This is called canonical lifting. But anyway, so the point is that the similitude group called GSPW will give you an automorphism of the metaplectic group. Okay, so there's other things like if your symplectic space have orthogonal decomposition into W1 plus W2, where W1 and W2 are both symplectic spaces, then you will have a diagonal embedding of SPW1 cross SPW2 to SPW1 plus W2. So this is nothing but SPW. So you will have a unique diagram, unique diagonal say, which makes this diagram commute. Where this, because this is the extension, MP is the metaplectic group is the extension, so the kernel of the product group will be Z cross Z. And the natural map from Z cross to Z, Z cross Z to Z is Z1 times Z2. Map Z1, Z2 to Z1 times Z2. So you have this kind of picture for multi-blocks. And to prove this, you use so compatibility of the Larray or Rao splittings with respect to the block decomposition. So it's in the book of section 6.224. Yeah, by the way, so basically if I can finish on time, then we will cover like 100 pages of Kudala Takeda's book. Okay, so I think the third one is a very interesting and important point, is about restriction of scalar. So if you have a finite separable extension of F, so right, any finite extension is separable if F has characteristic 0. Okay, so then you will have a trace map from K to F. It's just basically send every element X to the summation of home from K to its algebraic closure, and you will know that this trace purely it's an element inside K bar, but in fact it's in F. Okay. And so by precomposing the trace map, you can make an additive character of F into an additive character of K. So you can talk about so suppose you have a symplectic space defined over K. So you can view it as a symplectic space defined over F with the symplectic form, which is the original symplectic form. It's defined over K, right? Then you take the trace, it will be defined in F over F. So, right. So this is a symplectic. So this is a symplectic space defined over F, which is subfield. So in particular, the symplectic group for W defined over K is a subgroup for the symplectic space. Symplectic group defined over W. Symplectic space, a symplectic group of W. This is because if a linear transformation is K linear, then it's obviously F linear. And if it preserves the form inside, then it's also preserves the form of after taking trace. Okay, so you have this inclusion. So you have natural inclusion of this group to SPW. Then there exists a unique map IK which fit in the commutative diagram. This is called a base change embedding. And more importantly is that the Weil representation of this group is nothing but the Weil representation of the larger group restrict on the smaller group. Okay, so there's another construction called extension of scalar. So this is that if you have W, it's a vector space defined over F, and K is the extension field of F. Then we will have WK. This is just a W tensor with K, and you extend the product linearly. The symplectic inner product linearly. So in this case, SP2N or SP. Okay, so actually this you can think it's SPWK actually contains SPW as a subgroup. Okay, so then you will have also a unique extension, but because this is a subgroup, we can try to look at the preimage. So when the fact is that when this extension is even degrees, then the preimage is actually a trivial extension. When the degree is odd, the extension degree is odd, then the preimage is actually the metaplectic extension of the the symplectic group. Okay, so in particular, when K and F is a quadratic extension, you can consider this distinguishing problem for NP to NK and NP to NF, where K is a quadratic extension of F. So for example, the typical case is like F is real, the field of real numbers, K is a complex number. So you can consider a representation of the metaplectic group of complex number restrict on SP to NF. Okay, but I would like to say that, okay, so I think MP to C is actually a split extension of SP2 and C. So the reason is that you can further trivialize this Rauco cycle. Okay, so yeah, I will not go to the detail, but I think maybe, okay, so Gan Kudla Takeda's book is mainly focused on non-Archimedean local field. So I think maybe in the non-Archimedean local field, this problem makes more sense. But anyway, there's a question like this type of distinguished problem.
This case, I'm not sure your condition is multiplicity is true or not.
I don't know. It just mentioned that you can consider this question because
you consider the particle set decomposition. I would say that
this is a yeah. I think it's a very
yeah, it's not true. I mean, yeah, the old benefit is already at least two, right?
Yeah, and anyway, so there's questions you can start to consider. I think over finite field, there's no metaplectic group. It's kind of SP2N extension and over SP2NF.
The actually the characteristic in the F3. Is it going to be
I don't know. Yeah. Okay, so right, let's continue. So a very interesting fact about the metaplectic group is that two elements G tilde and H tilde are commute with each other.
Because the color is possible also put in the first time conjecture.
Oh, really? This is a
I think this is probably the proper element for the first time conjecture. You know, first time conjecture is G or GF.
G.
G.
Okay, Prasad conjecture. Metaplectic case of Prasad
Yeah,
conjecture.
this element, but his original conjecture is only for the vector group G.
Okay. Metaplectic.
Yeah, I think this is the property.
Case.
My question is this is the property.
Yeah, it's probably a valid PhD thesis question. Okay, so I think this the next point is quite important and interesting, is that when two elements in metaplectic group are commute with each other, the answer is that as far as they are commute, when project down to the symplectic group, they commute in the metaplectic group. Okay, so as a consequence is that is that you have a conjugacy class. You can describe the conjugacy class of the metaplectic group. So certainly So if you choose any element gamma here, so you can consider the conjugacy class of gamma, which is just G gamma G inverse when G running over all elements in SPW, then you can look at the preimage of this C gamma. So you have C gamma here. So the preimage certainly is the union of conjugacy class. The answer is that these are so each conjugacy class in the preimage is precisely parameterized by the center Z. So each conjugacy class is given by C Z gamma tilde, where gamma tilde is an arbitrary fixed lifting of gamma. Okay, so if you have gamma tilde mapped to gamma, then for different Z in Z, it will give you different conjugacy class in the Metaplectic group. So this is not very difficult, basically a corollary of theorem, of the above theorem. Okay. Right. So this finish everything about the basic stuff of Metaplectic group, and but we still have something to discuss is splittings, because it's a double covering. In practice, we still like to have a nice splitting so that we can work hands-on on this representation. Okay, so so one of the splitting is that we already discussed, actually used extensively in the definition of the Metaplectic group, is the splitting exists for the single parabolic, which means that you fix the polarization of the symplectic space, and you consider the single parabolic, which is a stabilizer of the Lagrangian X inside SPW. So this, as a matrix group, it looks like this, and maybe some C, and the C is symmetric matrix. So something like this. Okay, so the point is that under the Rocco cycle, this is not the Rocco cycle, but under the Larico cycle, so Lari's realization, you have this kind of splitting, and furthermore, it splits in the double covering if and only if -1 is the Hilbert symbol of -1 is equal to 1. So this holds for all cases when F has a residual characteristic 0. Okay. And right. But I think this one is -1 R. This one is -1. So therefore, over real field, this single parabolic does not split inside the Metaplectic to cover. Okay. So that's another interesting case of splitting, is that for the unipotent subgroups. So if you take arbitrary parabolic subgroup inside SPW, so this parabolic subgroup will look like a block matrices A1, A2 to AK, and some G0, and the lower part will be just determined by A1 and A2 AK. So A1, A2 to AK, and this one maybe it's I think, let me write in this way: G0 AK inverse star inverse A2 to A1 star inverse. And this part are 0 and this part are arbitrary elements. Of course, has some properties like this part determines this part. Okay, and something like this. But anyway, the unipotent subgroup is a subgroup inside a parabolic which are on the diagonal part they are all identity matrix. Okay, so there's a interesting fact is that N is actually inside a single parabolic subgroup. So there exists a X such that N, this unipotent part of a arbitrary parabolic subgroup inside the SPW is contained in the single parabolic of X. So we already know that you have a splitting from the single parabolic. So you can further embed N into the single parabolic and get a splitting. Okay, so a natural question is that if you choose different single parabolic, whether you get the same splitting. The answer is yes, the splitting is unique. Actually, you can choose different X as far as it contains N. So it will give you the same splitting. Furthermore, so this splitting is actually characterized by the property that this splitting is a group homomorphism and its image is normalized by the whole parabolic subgroup. So the image purely it's not necessarily normalized by the whole parabolic subgroup, but if it's normalized by the parabolic subgroup, then it gives you this characterize this kind of splitting defined here. And so there's one, I think, very interesting fact not discussed in GKT's book is actually occurred in Sun and Zhu's paper on conservation relation, is that this S actually glues into a well-defined map from the set of I believe that it's actually okay. So if you how do I say it? If you consider the union of all single parabolic subgroups, so then this splitting defines a well map, gives you different splittings for different choice of X glue together, give you a well-defined map from the single parabolics to the metaplectic group. Okay, so this consists actually a very large portion of the metaplectic group already, symplectic group already, but it's not contains the Weil group, Weil group elements, many Weil group elements, but it contains a lot of things. But the most useful one is that if you consider the unipotent elements, which means that elements taking certain power, okay, 1 minus the element. So what is the element is a unipotent. So G in G is unipotent if and only if G minus 1 to the power N is 0 for large N. So G here G always means SPW. Okay. So if you consider the unipotent elements, so this is, you can think as the union of all unipotent subgroups inside G. So then you will have a well-defined map from the unipotent elements to the metaplectic group, and such that it restricts on arbitrary unipotent subgroup is a group homomorphism. Okay, so there's explicit splittings even in the mixed model, but I will not discuss it. But the point is that in many cases, you want to discuss Whittaker model or generalize the Whittaker model, then you need a unipotent subgroup of inside Metaplectic group. So you would like to say that I can just take the unipotent subgroup of the symplectic group, and you take the canonical splitting. So this is a group homomorphism. So therefore, you can define generalized Whittaker models for the Metaplectic group using this canonical splitting. Okay, so there's another interesting splitting is that you can split for compact groups. So how do you get a compact group? The point is that you always fix a additive character psi, non-trivial from F to C cross, and C1 actually. And we recall that last time we have defined the notion of self-dual lattice. It is so we define L perpendicular. So this is a set of all W inside W such that psi pair with WL is equal to 1 for all little l in L. Okay, so this is the dual lattice of L. Self-dual means that L is equal to L perpendicular. Okay. With respect to the psi. And for the characteristic 2 case, you will need like further splitting like L plus and L minus. And right. But anyway, if you have a self-dual lattice, you can define SPL, which is a collection of all elements in SPW, which stabilize this lattice L. Okay, so this one is a compact subgroup inside SPW. Recall that here we have F is local non-Archimedean. Okay, so this is a compact subgroup, and it's actually a maximal compact subgroup inside SPW. Unfortunately, there's a lot of conjugacy classes of maximal compact subgroup inside SPW. This is very different from the real group case. So for real reductive group, there's only one conjugacy class of maximal compact subgroup. In the p-adic case, the set of maximal compact subgroup is in bijection with okay, so this is tricky. So all the maximal compact subgroup is a stabilizer of a point in the building. In this case, it has n+1 classes of maximal compact subgroup, and in this case, SPW case, type C case, it's simple that so the thinking diagram is given by this one. So, right, this is a thinking diagram of the extended thinking diagram. So I think this SPL is corresponded to this point, and so it's really depends on the conductor, the parity of the conductor of the character psi. So if for one parity, like even, it will correspond to this one, and another parity, it will correspond to another one. So there's even two conjugacy class of so-called hyperspatial maximal compact subgroup. So what is the definition of hyperspatial? Is that I think the simplest, most naive way to think about it is that in the hyperspatial case, SPL quotient out its pro-unipotent radical. Radical is isomorphic to a SP over finite field. Over Oh, okay. So SPL divides L divides PL. So this L divides PL will have a non-degenerate symplectic form. And so it's this kind of finite group. This is the case of hyperspatial. And in other cases, so this case is the reductive quotient of these points will be like a two symplectic group. Is it? Right. So only these two cases, it's a hyperspatial maximal compact subgroup, but it really depends on the conductor, the parity of conductor. Okay, in the characteristic 2, so you should consider this SPL2. But anyway, in the radial characteristic, it's odd case, SPL is equal to SPL2. Okay, then assume, let's make the life easier. Assume that the residual characteristic is odd. To be honest, there's almost no breakthroughs or serious discussions for the, except works of Takeda. No serious discussions for the lattice models of residual characteristic equal to even case, I think. So there's yes, why not?
Yeah, then
You can take a lattice as far as this lattice cross F give you a maximal like I think a maximal abelian. You can use the induced model to get the induced models, and you can translate it into a lattice model.
then the question is the characteristic 2 is going to be more trouble, I guess. More troublesome.
Yeah, so that's why I think that's why Takeda introduced this SPL2, this group, so that on the SP, so that there will be a nice splitting on SPL2. And in particular, he can define a splitting in the Schrodinger model, actually. This is given by this one. Okay. Where who is here?
This is 2 to none, one is 2 equals the other is 2.
No. Because you should preserve the lattice. Multiply by 2, preserve the lattice. Multiply 2 inverse.
The 2 is only if you assume.
But the lattice does not preserve that. 2 inverse times L is not equal to L.
I think 2 is the
2 is
if you assume the residual characteristic odd, then the 2 is always
yeah. When residual characteristic is odd, so these two groups are the same.
Yeah.
Okay. When it's even, then these two groups are not the same. Yeah. So in general, so you will have a splitting like this, but when residual characteristic is odd, then these two groups are the same. So I just write SPL to the Metaplectic group. So you will have a splitting, and this splitting is actually a group homomorphism. So this is what they proved in the book. Because SPL is almost perfect group, except of course you have a very headache case is that the case that dimension of W is equal to 2 and the residual characteristic, a residual field of F has 3 elements, then this group is not perfect. Okay, SPL is not perfect because its reduction more P is not perfect. Except this case, you will have a unique splitting from K, from this K is this one, okay, to the Metaplectic group. Okay, again, because the perfect group stuff. the splitting is unique. Okay. Even in the characteristic case, residual characteristic case class is odd case. So okay, so this is a splitting, right? On the other hand, you can consider the lattice model. So this lattice model is given by this way, is that you have LHLs and you have the induced model like this, and what you do is you again, just like the Schrodinger model, how do you get the cross section of SPW to the metaplectic group? For the concrete realization is that you just left translate of this function and do integration along the lattice. Okay, so this intertwining operator will have a nice property that when it's restrict on SPL, it is just a translation of the function by left translation of the function, because K SPL is SPL2 is actually acting on HL. This okay, acting on HW, this group. Okay, so then you just use the left translation. So this gives you a geometric model. So so in work of the joint work with Hongyan and Savin, we actually extensively use lattice model to study theta lifting. Okay. So similar to the Sun and Zhu's result, actually, if you consider for each at least in the residual characteristic odd case, okay, for each L, each self-dual lattice, you will have a splitting. So then these splittings will glue together into a well-defined section of along the union of all this kind of SPL groups. Okay, so in particular, these elements are what should I say? So the set of these elements contains all topologically unipotent elements. What's the meaning of topologically unipotent? It means that if I take the do I need to take? Okay, so topological unipotent means sorry, I think I made a mistake here. So it's just like unipotent means that x minus g minus 1 to the power n is equal to 0. But now I allow n goes to infinity. So topological unipotent, x topologically unipotent means that limit of n goes to infinity of x minus 1 to the power of n is equal to 0. Okay, so if you happens to know the theory of semi-simple character, or know a little bit about construction of positive depth supercuspidal representation, or positive depth representations, then you will know that there's something called minimal K-type, and there's a generalization of minimal K-type called a refinement of a minimal K-type is called a semi-simple character. So in this case, because this kind of canonical splitting, you can define semi-simple character in a canonical way.
In this case, you have also like two complete calculation for the because result generalized to the
No, this is different. This is topologically unipotent. It can be semi-simple.
Yeah, I'm not. The structure. You know the because the.
I know that this one,
Yeah.
but
So I think you also can use the uniqueness structures to link into the finite group to the whole package. That's what you.
I think what you mean is that you can lift the Becker's
I
parameterization
think here you have
to the Metaplectic group.
Yeah, I think here you are going to say like.
Yeah, but
It's big
yeah, yes,
over this all.
topological. But there's a natural bijection between the unipotent conjugacy class in MP and the SP,
Yeah,
right? Even by this kind of Siegel splitting, right? You already see these bijections.
so I would need a.
You don't, but you are saying that using the topological unipotent one, you can translate the Becker's result. Yeah, I think so.
Say for example, I assume this is probably even true for more general, like not a double covers, even more like.
Arbitrary.
Because
finite
here
cover.
the topology quantity, you are quite relies on the cosine-cos relation, right? Because eventually I'm trying to say is that if you look at the p-adic field, you have n-fold cover in general, as long as you take the power, the depth is larger enough, the cover is going to be split.
Yeah.
This is certainly true for almost.
I think that as far as the cover, the center has the order co-prime to P, then it should be okay. It should be split. But the question is whether you have a canonical splitting.
Yeah, you're.
Okay, so there's a lot other things like the topology and the measures on the Metaplectic group. So the point is that as a topological space, the covering is not a product space. So this is how to understand it. If it's a product space, then it means that the Metaplectic group is a disconnected group. It supposedly say is, so in the case that say is equal to mu2, then Metaplectic group is disconnected group, right? Because mu2 is disconnected. But actually this Metaplectic group is a connected group. Okay, so I should not explain it in the p-adic case, because p-adic group is a totally disconnected group. But suppose let's see in the real group case, SPR NR to NR is connected, and if as a topological group, NP to NR is is isomorphic to the product space, then it should be disconnected. But actually, NP to NR is a connected group. So therefore, as a topological space, they are not isomorphic. However, as a measurable space, they are isomorphic to each other. So because it's basically saying that ignore the measure zero parts, it's still like a product space. Okay. So there's other stuffs like Weil representation. I think I have already explained that how do you do the Weil representation is that you for each Heisenberg Weil representation of the Heisenberg group, you will have a natural embedding, canonical embedding, and this embedding is unique, and then you just let it acts on the Heisenberg group, Heisenberg representation. And so the one of the question is that if you change the additive character, what will happen? So it's easy to see that if you change the additive character from psi to psi a square, where recall that psi bx is just a psi b times x. Okay, so then these two representations are isomorphic. In fact, this is the if and only if condition. So all edit, once you fix psi, which is F2C1 non-trivial, we assume F is local or finite. So then the all non-trivial additive character of F is in bijection with psi A, where A is inside F cross. Okay, so this set is in bijection with F cross basically. Okay, so it's also natural to ask this question, but the answer is let me try to the answer is here. So if you have two additive character, psi A and psi B, so when these two Weil representations are isomorphic, the answer is that if and only if they are differ by an element in the square, which is a square element. So there's other isomorphisms, like if you take the conjugation of the Weil representation, then it is just a complex conjugation of the Weil representation, and it is Weil representation of the complex conjugation of the character psi, but now you want say x by say bar, so you have to precompose automorphism of MPC. So if it's double covering, then there's no need to compose this iota. Okay, so what else I want to say? Okay, so we have a Schrodinger model, and you can write a see a very explicit formula of the single parabolic action on the Schrodinger model. Okay, in the Schrodinger model, basically element in the Heisenberg representation is a function with complex support and a locally constant complex support function on Y. So the action, the essential part up to the normalization constant here. So the essential part is just multiplied by A. Okay, and so this determinant is responsible for to make this operator to be a unitary operator. So you just scale the function, it will not be a unitary operator. So you have to multiply the norm of an element times to the power of half. So that make it to be a unitary operator. And this one is responsible for the for it to make it to be a splitting. Okay, to make it to be a group homomorphism basically. And the unipotent part acts by multiplying the function by a quadratic character basically at each point. Okay, so that's why if you, in many cases, you are forced to evaluate some function, evaluate this operator at certain specific test functions, then you will see some kind of Gauss sum. This is because you will see this one. And then there's another important thing is that when this, if you have Wi, it has a form that I think the point is that W can be written as E1 to EI, and direct sum with some W0, direct sum with F1 to Fn. Then you can switch these two parts. Okay, so I think I'm writing something like this. I of I minus I, something like this matrix. Then the action will given by essentially its partial Fourier transform, but up to for eighth roots of unity. So this is an explicit formula for the Schrodinger model. So my advice is that, except necessary, never use this explicit formula. Okay, so one more comment is that actually you, instead of consider just a wave representation, this representation can be paired with the Heisenberg group so that you can get a semi-direct product of the Metaplectic group with the Heisenberg group, and it acts on the Heisenberg representation. So this is called Heisenberg wave representation. Why this is useful is because you have also something called a mixed model. It says that if you have W, you take a maximal, you take a isotropic subspace X, and you take a complement of also another isotropic subspace X star, so that X and X star has a perfect pairing. Then you will have a natural space that it will uniquely determine the space W0. It's perpendicular to X and X plus X star. So you have this kind of decomposition. And then you will have a parabolic subgroup. It's again a maximal parabolic subgroup inside SPW, has a form that it has Levy like AG A star, where this little g is in, this little g is inside SPW0, and the A is in GLX. Okay, so this is the Levy part, and the unipotent part will be matrices looking like this way. Right. So if we use the Larry invariant by certain good choice of the realization of the Metaplectic group, then you can see that. So you again have a very explicit formula of the Levy part and the unipotent part act on this mixed model. Okay, so in this case, the wave representation is realized as a function on X star and taking value in W0, where W0 is a wave representation. Okay, look this part. So is a wave representation of the smaller Metaplectic group. So it's a function, a vector valued function on X star. Okay, so then the action of AG, basically MAG, is as a function part, it's again just the scaling by A star. And so you also have a normalization like this. And then because it's vector valued, so in each point at this vector, you act by the wave representation of the smaller wave group, Metaplectic group. So you have this W0, G1, okay, something like this. And the unipotent part, again, it's like act by a quadratic character. Okay. And but for this C, it will be the Heisenberg group action on the vector at its value. So this is the formula. Okay, so these are very useful. I think essential if you want to compute the generalized Whittaker model for the wave representation. This formula in the calculation in the mixed model. And the mixed model is a very important trick in the in local theta. Okay, so there's also explicit formulas in the finite field case, and you see because in this case, this wave index can be explicitly computed and expressed in terms of Legendre symbol. So you will have this kind of beautiful formula for the Schrodinger model. And so hopefully I can finish in 5 minutes. Is that so? There's another generalization of the lattice model is called the generalized lattice model. So look, in the lattice model, we require that L perpendicular is equal to L. Generalized lattice model, we only require L perpendicular is contained in L, but it should not differ from L too much. It still should contain PL. Okay. So this L perpendicular and L are not differ too much. It's just a differ at most times one uniformizer, basically. So the point is that L divided by L perpendicular is again a symplectic space, but over the residual field. So therefore, you can define Heisenberg wave representation for the symplectic group over the residual field. And the generalized lattice model is realized as a locally constant function W on W, which is a symplectic space to the concrete model of to any model of the Heisenberg wave representation over the finite field of this finite group. Okay, so this S is a finite dimensional vector space, basically. Okay, so you see in the lattice model case, L divided by L perpendicular is just zero space. Then the wave representation is just a trivial representation. So this definition is actually recovers the lattice model, and it specifies the equivalent relation like this. Okay, so then you will also have a splitting, which is given by this kind of integration formula. So you can check Pan Shuyan's paper on this. Right. So the nice part is that when restrict on SPL, so its action is just by translation of the function and the Heisenberg wave action on the fiber. So it's a most naive action. So yeah, Hong Lok and I, we use quite a lot of, also Pan Shuyan, use quite a lot of this generalized lattice model to study wave representation, local theta. Right, okay, so I have mentioned a good lattice. So for the symplectic group, so the collection of maximal compact subgroup of SPW is equal to the collection of SPL, where L is good. Okay, so if you take all the good lattices, then it will give you the all maximal compact subgroups of SPW. Where SPL is just the element to stabilize this lattice. This almost, yeah, this also even holds for the orthogonal group and the unitary group. So the last thing is that we have constructed this wave representation, but this wave representation as a representation of Metaplectic group is not irreducible. It's reducible. It's decomposed into two pieces. So how to see it? One way is that you realize it on the Schrodinger model, then it is just nothing but functions on Y. And so you can consider even functions, space of even functions and the space of odd functions. So even functions is just the function satisfy that psi minus y is equal to psi phi y. Okay, all function is phi minus y equal to minus phi y. So these two spaces, if you just, I think you just look at this formula, you see that all these actions preserve these two spaces. So therefore you see the wave representation decomposed into two sub-representations. One is even, one is odd, space of even function, and another is space of odd function. And the fact is that actually these two pieces are all irreducible and they are not isomorphic to each other. And even furthermore is that if you take L is self-due, then this even way representation is spherical, means that it has a unique vector which stabilized by SPL. And the odd way is non-spherical. So, right, that's it. Okay, thanks.